Continuing talking about Newton's laws, again, this is going to be quite the lengthy discussion about Newton's laws because Unit 3 is Newton's laws, and then our Unit 3.5 is application of Newton's laws. And so we're just kind of really trying to dive into a deeper understanding and of his 3 motion-based laws, not as much with his gravitational law. Remember, it's the interactions. The force should be a repeat that is a push or pull, and this is why science can't suck, because it's only a push or a pull upon an object. And the big part of this truly is interactions. If you notice that is italicized, that it's the interaction with another object. Whenever there's an interaction between objects, there is a force upon each of the objects. When the interaction ceases, meaning it no longer exists, the force no longer exists there. Okay, the fact that it's still moving is a product of that interaction. And if there is no friction, that object should continue to move. But we know that friction is real, and it's a real big issue with us when it comes to modifying and changing things. So we need to make sure that we account for friction. We will go into, in applications of Newton's laws, we will dive deeper into the calculations of friction so that we can use it and modify it then. So, in a way, how we do this is done by what's called a free body diagram. And we're using Dexter here as an example of a free body diagram. The arrows that are placed around Dexter are the normal arrows that you would see on a free body diagram. The free body, and this would be for your more basic XY axes that we normally see, because most of the motion that we deals with the X and the Y axes. That does not mean that an arrow cannot go diagonal. It can. And sometimes it's best to draw out that arrow diagonal, and then in a separate free body diagram showing everything as a separate X and Y, because that's ultimately what that diagonal is. It is there's a force in the X and a force in the Y to make this diagonal, and it can be in any direction. I just chose that one as well. And so we start to understand with sometimes some of these free body diagrams why sometimes it's easier to pull an object as opposed to pushing an object based on the interactions that we see. And so that's what we look at with a free body diagram. And again, you do not, the free body diagrams can be very simple. They can be, a lot of times I like to use circles, but I really like to use boxes. I like to use boxes a lot because it allows us to see objects moving left and right easy, objects up and down, just like we have shown with Dexter here. And then when you have things moving at an angle, you can kind of guess the angle well if you drew out a reasonable box. So the diagonal angle on the box is probably approximately 45. And then I think sometimes you can add your X and Y axes a little bit easier from that. Some people like to draw the same things but using circles, and the same thing applies, where you would have your x-axes, y-axes, and maybe some people like the circles because you have that option to basically almost making the angle sign inside that triangle with that. And some people enjoy that part of it or utilize that part. I think sometimes the object that's moving dictates kind of the circle or a square that you draw. Sometimes I will draw two of them, one with a little bit more, you know, if I might draw a car, you know, just that very rudimentary car drawing that might be there to kind of indicate like, okay, it's moving, what's going on, and so that I can draw some other things in it. But again, it does not need to be extremely elaborate when we're drawing free body diagrams, because sometimes the forces can become, you can have a lot of arrows involved, and therefore having the more elaborate your drawings are, the more busy it becomes, and therefore opportunities for us to not kind of really shrink it down to what is actually going on and what's happening at that time. So kind of the step-by-step of it all is to, you know, draw. If you have more than one object, it's best to draw more than one free body diagram. And with that means showing all the forces acting on that object. Try to adjust for magnitudes. And why do we say that? Well, if we have a object sitting on two objects sitting on top of each other, okay, we have multiple interactions. You know, maybe they're sitting on a table, but I just drew it on that gray line at the top there. You know, if let's color it in. So now we have a red box and a green box. The forces that are involved here, and sometimes you might even be able to say, okay, for the free body diagram of the blue box, I'm just going to draw a blue box there so that I'm able to keep that separate. That's why, you know, multiple color pencils, colored pens, notability, whatever it may be to help you out with that. You know, you're going to have the weight of the blue box, but we're also going to have, you know, the weight of the green box. It would not make sense if we're told one thing and another to write, say, oh, there's the normal force of the green box on the blue box. If the green box weighs less than the blue box, that interaction should not be larger than the weight of the blue box then. And some of that, again, comes through practice. So drawing them out and the magnitudes as best that you can. That's why it was suggested that you have a protractor so that you can kind of scale things out in a way for you. And so that hopefully helps. Labeling the forces is going to be a big one, because labeling your forces helps you keep things in order and in check so that you know what's going on. And then if there are any that are at an angle, that you resolve the vectors for them. Now, a lot of these are also going to be at 90-degree angles, which is going to be very nice for us, but then there's going to be some times where we can't guarantee that it's a 90-degree angle or makes a right triangle, so therefore we would have to use the law of sine or the law of cosine depending on what we're given. We also want to make sure that we apply Newton's laws. This comes into a lot of play when we get into Newton's third law, because we will want to make sure that we identify our Newton's third law pairs so that we can work with that and kind of go through there. Drawing them out as close to with their magnitudes and directions as much as possible will allow you to see in your free body diagrams if what the net force kind of is almost doing. And remember, if the net force is 0, okay, so if the net force is 0, there's no motion. It's not moving. Or if it is moving, there's something opposing. Okay? There's no acceleration. So here is a way to label them. Another method to label is sometimes the force, and they're just using F as a general force is acting on it. So the label of F is just a general there. We will utilize some of the letters that we saw in that larger diagram, but A on B can be done just as A, comma, B. But really what it comes down to is we need to begin like something on something, and it's usually always by on, meaning A is interacting with B, meaning when we draw a free body diagram, especially ones that have multiple ones, that everything, if this is box B and this would be box G, there would be weight of Earth on B. And so over here, we would say weight of Earth on G. So everything in this box would end up or should have the ending of G. And that also allows you to see if you've placed all of the forces, all of the interaction pairs in there. Now, some interactions are not you would probably guess to be Newton's third law pair, because Newton's third law is usually fairly well known that for every action there's an equal and opposite reaction. Well, when we deal with free body diagrams and we have an object sitting on a table, the weight of the Earth acting on the box goes down, as it should. The normal force of the table on the box, those are not Newton's third law pairs. Yes, there is a reaction for that action, but a action-reaction would mean you would need to have an interaction between two different things, such as an example of that we had earlier, or that I kind of used earlier, kind of the blue and the green boxes. There would be a Newton's third law pair. The green is interacting with blue, and the blue is interacting with the green. Okay, there is a normal force interaction there. The weights of the Earth on whatever are never a Newton's third law interaction. Okay, there would not be if it's a normal force of the table on the box, as we have here, that's not an interaction. You would actually need to draw Newton's interaction or a free body diagram for the table on the box. Well, at some point in time, we have to identify our system, and this is what we talked about early on, was frame of reference. What are we using as our frame of reference? Because as you can probably guess, this can become engineered up way quick. But we're trying to keep it simple. Okay? With that, it allows us to kind of, what's our frame of reference, focus and put blinders on in some way to any of the other interactions that might be happening, but we're only going to focus on a small area. Okay? Because that's going to allow us to kind of work with what we need to do. Otherwise, things can become way too elaborate, and then what do we do? And then it becomes too hard to solve. So for the last little bit here, in the chat, please add how many interactions there are for the frame of reference inside the green circle. When we look at this, I'm going to draw a very simple free body diagram for Dexter. I'm going to draw a circle because Dexter's a human being. We know we will have the weight of Earth on Dexter. But Dexter's standing on a box. Therefore, we have a normal force of the box on Dexter.